All right, now that we finished all the lathe work on our part, we're going to complete the part on the milling machine. Before we took it off the lathe, we faced both the front and the back surfaces of the part, making them parallel to each other, and that's going to allow us to easily clamp the part in the milling machine vise. To do so, I'm going to grab the speed handle, put it on the vise. This allows me to open and close the vise jaws. I'm going to open the jaws. I'm going to wipe the jaws out. And I'm going to put the part inside the vise, left and right. I'm just going to eyeball it. I'm going to center it. And vertically, I want to clamp the part so that we can see the center hole. And that allows us to see when our cutting tools break through into the center of the workpiece. So I'm going to clamp the part, put 30 or 40 pounds of force on the vise handle, and then put the vise handle away. So we're starting with the side holes on the part. They're specified as 1024 UNC through. Based on the drawing, I can tell that the threaded holes go through one half of the part, but not the second half. Okay, to make this part, or to begin cutting these features, the first thing we have to do is set our datums in the X and Y direction. When we're using the lathe, the tailstock is always set so that it's collinear with the headstock. So on the lathe, we never had to worry about setting a 0 for our drilling operations. The tailstock always drills right through the center of our part. On the mill, however, since we have two axes of motion, the table moves left and right, and the saddle moves the table and the vise front to back. Since we have those two axes of motion, the X and Y, we need to set some datums before we begin. To set datums on a milling machine, one of the easiest ways to do so is to use the edge finder, or an edge finder. There's two types, conical and cylindrical. I'm going to demonstrate by just loading it and showing its use, because that's the easiest way to understand the function of that tool. I'm going to move the spindle off the vise. I have everything set, have the spindle raised and locked so I can safely load my drilling chuck. That's what we're going to use, just like we used a drilling chuck in the tailstock of the lathe. I'm going to load the drill chuck. And now I can easily load a variety of measuring and cutting tools into the spindle. I said I'm going to start with the conical edge finder. You can see that the edge finder, the bottom of it, is spring-loaded, and it moves radially with respect to the top portion of the edge finder. Okay? The very bottom has this conical profile, this conical geometry ground into it. And I'm just going to demonstrate its use so that we can understand why we would use this type of edge finder. In this case, we're going to locate the outside edges or surfaces of our cylindrical workpiece so that we can set the center in the X, the center of the part, the center of the cylinder in the X direction. We can set that plane as our X0. So I'm going to come over towards the part. I'm going to lower the edge finder towards the part. I'm going to lock the spindle from moving up and down. I'll move away from the part. Okay. And to use the edge finder, we always begin by gently pushing it off center. So you can see I've pushed it, I've displaced it, so when it rotates, we will see a large eccentricity. I'm going to do the 3-step check on the milling machine before I turn it on. I'm checking visually to make sure I have clearance between, in this case, the edge finder and my workpiece. I'm checking to make sure the machine's in high range. Then finally, I'm going to check and make sure that I turn the machine on in the appropriate direction, which is clockwise, as viewed from the top of the spindle downwards. Okay? I can adjust my spindle speed. For the edge finder, we generally want to use a speed between 1,000 and 1,200 RPM. I'm going to move the edge finder over into gentle contact with my workpiece. And as I do so, we will visually see the eccentricity of the edge finder begin to decrease. So I'm moving the same direction. You can see it looks like the edge finder is just about perfectly on center. And if I keep going the same direction, you'll see the edge finder suddenly kick out to the side. In this case, when I say the side, perpendicular to the direction that I'm moving. Okay, so we saw it kick out in the y-axis, y direction. I'm going to back up and repeat that so you can see it one more time. I move away from the workpiece. I gently move into contact with the workpiece. Now as I move over towards it, the eccentricity starts to decrease. If I keep going, albeit very slowly, I'm going to reach a point where the edge finder jumps out suddenly. I'm going to seesaw motion, and that is going to be the point at which I want to zero my digital readout. Since I'm moving in the x direction, I'm going to zero the x-axis on my DRO. Excuse me. Now, I'm simply going to move away from the workpiece, or move the workpiece rather, away from the edge finder in the X. I'm going to move around the front of the part, and I'm going to reapproach it from the other side of the part. Each time I move, I want to remember that it's the part and the vise that are moving, not the spindle. Okay? I'm going to use the right-hand rule. I want to move the part back towards the rear of the machine, towards the column of the machine. So right-hand rule tells me that clockwise is going to be the correct direction. Now I want to move the part to the right. So on the dial, on the hand wheel for the x-axis, counterclockwise is going to be appropriate. And I'll use the right-hand rule every time I move the x or y axes on the milling machine. I'll move back in on the other side of my part, and I'll repeat the sequence where I gently come into contact with the part. I bring the rotating edge finder into contact with the part. I slow down, and now slowly I move towards the same direction. I keep moving the workpiece towards the edge finder, and eventually we're going to see it kick out to the side. Okay, on our camera, it's kicking out to the back of the part, so it's a little harder to see. I'm going to back up and repeat. So I'm close to it. I keep moving. Oh, sorry, let me show you this way. I move up to my part. The eccentricity starts to decrease as I'm approaching the center of the edge finder being on the center of the surface. I continue motion in that direction, and the instant that it kicks out, I stop. In this case, I don't want to zero the reading on the x-axis of my DRO, but rather I want to take half that value. I set the right side of my workpiece to 0. I've moved around to the left side of my workpiece. So now whatever that chord length is, I want to take half that value, and that will be the exact center line or center plane of my cylindrical workpiece. This DRO has a convenient feature for doing this. It's called the center line feature, or CL. So I'm going to push that. Then it wants to know which axis. So the x-axis, when I push the button, we'll see the DRO change to half that value. Okay, it changed to half. Now, if I move away from the edge finder, I move my part away from the edge finder, and I move it around to the front of the workpiece, and I move to my XDRO location, showing 0. Or close to it. Okay. If I turn the milling machine off, it's a lot easier to hear me as well, and I center the edge finder up, just for a reference mark, to see if I have a gross error. If I bring this over close to my part, I can see from my point of view that I am on the middle of the part, the center of the part. This edge finder, these mechanical edge finders, when they're used properly, meaning you move slowly once you get close, and then you stop motion immediately once you see it visually kick out to the side, if you use it that way, using it properly, then they have a repeatability that is better than 1/1000th of an inch. So they are very accurate considering how simple of a mechanical device they are. Okay, I'm going to move the spindle off the vise because I want to switch tools. Actually, it might be easier to use the higher portion of this edge finder as my cylindrical edge finder. Nope, I'll switch to my other one. So I'm going to take this conical edge finder out, and I'm going to load one that has a cylindrical tip instead of a conical tip. It's going to work the same way. But this time, I'm going to set my other datum, which according to my part drawing, is the back surface of my workpiece. So this rear surface, this rear plane, is to, the goal is set that as my Y0, my Y reference plane. So I've got the edge finder mounted. I'm going to move into position towards the back of my part. I'm going to raise the spindle because I want to use the small portion of the edge finder, the smaller cylinder. It measures exactly 0.200 inches in diameter. That's going to be important in a minute. Okay. I'm going to use it the same way with the machine off. I'm going to gently displace the edge finder. I'm going to lower it so that a portion of that small cylinder is going to contact the rear face of my part when I bring the part into contact with it. I can see that I have plenty of clearance between the edge finder and the workpiece. I'm in high range, so I'm going to turn the machine back on in the clockwise direction. Now I'm going to move the part gently into contact with the rotating edge finder. And we're going to do the same technique that we used before. We're going to continue in that same direction until the eccentricity decreases to the point that it looks like it's almost perfect. And then I'm going to slow down my motion, but keep moving the same direction. I'm moving the part towards the edge finder, or I'm moving that rear plane of my part towards the spindle center line. I keep doing so, and the instant that I see the edge finder kick out to the side, which is right there, I'm going to stop my motion, and in this case, I'm going to zero the Y-axis datum on my DRO. Okay, if I back up and I turn the machine off and I displace the edge finder again and I repeat this, the sequence, gently coming into contact, moving slowly while I watch the eccentricity decrease. Once I get close to it looking perfect, I'm going to slow down. Very slowly keep moving the same direction, and the instant that I see it kick out to the side, I'm going to stop motion. Okay, so I stop motion, and if we look up to the digital readout, you can see that it's exactly in the same location that it was when I set my zero. So again, the edge finders, they are very repeatable and they're very accurate. I'm going to move away from the part, but I'm not finished yet. Since this lower cylinder has a diameter that's 0.2 inches, once that edge finder triggered and I was on my zero position, which I'll return to, once I was on my zero position, the goal is to make the rear plane of my part, which matches the datum on my drawing, the goal was to make the rear plane of my part match the center line of the spindle. Okay, but if you think about it, I am not in that location right now. I am offset by a value, by a magnitude exactly equal to 1/2 of the diameter of that edge finder cylinder, that lower cylinder. If I raise my edge finder up, I need to drop the part down a little bit to do this. If I raise it up above the part, I need to bring the workpiece, I need to feed it towards the spindle center line, a distance exactly equal to the radius of the edge finder, or 0.1 inches. So right hand rule tells me I want to move the part backwards. I'm going to turn the Y-axis, the Y-axis hand wheel, clockwise, so I know I'm going the right direction. And I'm going to watch the DRO for my magnitude. I'm going to move exactly 100 thousandths, or 0.1 inches. And now I'm going to re-zero the value shown on the DRO, because this is the location at which the center line of my spindle is coincident with the rear plane of my workpiece. Okay, so anytime we're using a cylindrical edge finder, we always have to remember to offset for the radius of the cylinder, the radius of the edge finder. Now we have both our X and our Y datum set, so we can commence with the drilling sequence. I'm going to move the spindle off the vise. The edge finders are not sharp, so I can handle them without any risk. I'm going to hold the edge finder in one hand, loosen the chuck with the other, and I'm ready to load the first tool in the cutting sequence, which is going to be the center drill, because I want to accurately locate the two holes that we are about to create. So I clamp the center drill. I clamp the center drill, and I move into the correct position based on my part drawing. The location of my first hole will be X0, meaning the center line of the workpiece, Y 0.75 inches. So X0, Y 0.75. So X0, I move the Y down 3/4 of an inch. Stop when I get close. And my tolerance for the position of these holes is plus or minus, let's see, in the X direction, I'm plus or minus 5 thou. In the Y direction, I'm plus or minus 20 thou. Okay, so I'll come in close. So if I'm within 1 thou or 2, then I'm plenty close. So I'm at X0, Y 0.75. I'm ready to start my first hole. Okay, if I flip to the speed chart that's near the DRO on the milling machine, I can check that this center drill, it has a tip diameter that is about 1/8 inch in diameter. Since we're drilling aluminum, our speed chart tells us that it recommends about 1600 RPM for the appropriate spindle speed while drilling this size feature. So I'm going to turn the milling machine on and then adjust the spindle speed once it's running to 1600 RPM. 3-step check. I've got clearance. I'm still in high range, and I'm going to turn the spindle on in the forward or the clockwise direction. I'm going to adjust the spindle speed to 1600 RPM. And now I can check my DRO. You can see it moved just a little bit because the DRO is very sensitive. We know the piece of paper is about 0.003 of an inch, so there's always going to be a little bit of fluctuation unless we lock the axes in place. There are little levers to lock the axes, but our tolerances aren't small enough to have to worry about that right now. Okay, so I'm going to bring the tool down to the part, create a little target mark. I'm going to apply a little oil to the target mark, and now I can commence with the center drilling. So you can see the chips coming off the center drill. And again, the goal by using the short and stiff center drill is to create the initial crater for the hole in exactly the location that the DRO tells us the machine is in. That's the first one. The second hole is at X0, Y minus 1.25. So I go down to 1.25 inches. Again, within a couple of thousandths of an inch is fine. 1.25. There we go. And I do the same thing. Come down, lightly tap my part, put oil on that target mark, and then commence with the center drilling operation. I'm using peck drilling to help the chips evacuate out of the hole. Okay, I'm finished. You can see that the spindle on its own, it wants to fall down because of the weight of the drill chuck. So I'm just gently putting a little bit of force, a little bit of pressure on the quill lock. Okay, I can still overcome it very easily with the quill handle, but the little bit of pressure will keep the spindle from dropping down as I move from one hole to the next. I'm finished with this tool, so I can stop the machine, use a rag, I can wipe the chips off the drill. Just like on the lathe, I'm going to teach you to always use a rag when you are taking the drills out of the machine. because they could have chips on them, but more importantly, they can be quite hot once we start drilling deeper holes or work with, when we're working with tougher materials like steels. So that was the center drill. Next, I'm going to use the .157 tap drill. My hole note tells me the correct size tap drill to use for this hole. I load the .157 drill bit, and again, the tap drill is simply the final size that we drill the hole in preparation for threading it with a tap. So if I move this tool over towards my workpiece, we can see that it's a lot longer than the center drill, and it's going to collide with my part unless I lower the knee on the milling machine, which lowers the saddle and the table and the vise and the workpiece. So I'm going to lower the workpiece using the Z-axis handle. I'm going to move back over to X0. I'm still at Y, 1.25 inches, so I'm still at location, at the Y location for my last hole. I'm going to put a little oil in those previous 2 craters that we created. I'm going to turn the machine on. Then my speed chart tells me that I would slow the machine down to about 1500 RPM. It's not a big change. I'm going to release the quill clamp and commence with my drilling using the tap drill. You can see the chips coming out, and you'll see me using the pecking motion. Each peck, or rather I drill a distance, a maximum distance that's about equal to the radius of my drill bit. Okay? And then I retract the drill bit to help the chips evacuate. I can feel the drop in resistance, and I can see the drill bit entering the center hole in our workpiece. So I'm all the way through the top half of the part. I'm going to raise the spindle and lock the quill clamp. Now I'm going to move into position for my second hole, which is Y, 0.75 inches on my DRO. And I will drill the second hole with the .157 tap drill. You can see the chips coming out, breaking into nice little pieces. That's what we want to see. If you don't see the chips coming out, that means they're getting clogged, and they can cause the drill bit to overheat, expand, seize in the hole, and break off inside our part, which is never what we want. So always use the pecking technique that I'm demonstrating as we make these parts together. So I raise the spindle, I'm going to lock it in its upright position, and I can turn the spindle off. I'm ready to move back off the vise, or rather, when I say that, you know what I mean. I can move the part and the vise out from underneath the spindle. Okay, it's always the part, it's always the vise, it's always it's always the table and the saddle that are moving around. It's never the spindle. You can see the spindle is rigidly connected to the column and the overram on the mill. Okay, I'm going to use my rag. I'm going to hold on to the drill. I'll release it from the drill chuck. And I'll wipe off the part. We have done everything we can that is a drilling operation. Excuse me. Sorry. We've done everything we can that's a drilling operation. Now we are ready to cut the threads into that workpiece. To do this, we want to remove our drill chuck. So I'm going to follow the 5-step procedure. I've got the machine off. I've moved the vise out from underneath the spindle. I'm going to raise the spindle and lock it. Okay. The drill chuck is not sharp, so I can grab it with one hand, and then I can use the automatic drawbar controls to eject the drill chuck from the milling machine spindle. So I remove the drill chuck. I'm setting it down over here for the sake of the video. And the next tool that I want to load is a spring-loaded center or spring-loaded tap guide. It is a cylinder that has a point on the end, and just like the edge finder, the easiest way to demonstrate its use is just to show you. So I'm going to load a 1/2-inch collet into the spindle. I'm going to load the spring-loaded tap guide into the collet. I'm going to lower the quill clamp and bring the part back underneath my spindle. I'm still at Y, 0.75 inches. So I need to move the X over to 0 inches on my DRO. Oops. Right about there. Okay. Next, I'm going to grab a 1024 UNC tap. And I'm going to grab a tap handle. I'm going to put the two together. The tap handle is the tool that is used to provide the torque, to provide the rotational twisting force necessary to cut the thread on the tap into our previously drilled hole. I'm going to put some oil on the tap. The back side of the tap handle has a countersink in it, so I can engage the spring-loaded tap guide. I can pick up the tap, and I can put the tip of the tap in my hole. The spring-loaded tap guide is now going to hold the end of the tap handle perpendicular, or perpendicular to the surface of our part, or you could think of it as it makes sure that it maintains, it keeps the axis of the tap parallel or collinear with the axis of the hole that we've drilled. Okay, so this is very important. If I've got a surface, a part that I drilled a hole in, and now I'm trying to cut threads into it, if I try and run the tap in at an angle, the tap is going to try and twist, and it's going to break. So it's always very imperative that we hold the tap perpendicular to the part surface, or you can think of it as collinear because we've got a cylindrical surface in this case. Okay, I've already put oil on the tap. You can't have too much. And now I'm going to do this manually. I'm going to use the tap handle to rotate the tap. And once I feel increased resistance, I'll back up about half a turn, and then I'll continue in the forward clockwise direction, and I'll rotate the tap. The tap is tapered so that it gradually cuts the threaded profile, of the whatever thread it is meant to cut, whatever is written or laser etched onto the tap. It's tapered so that it gradually cuts that profile into the previously drilled hole, the hole we drilled with the tap drill. So I'm going to go forward and then back up half a turn, forward and back up half a turn, and I'll continue until I'm all the way through the section of our workpiece that we drilled. This is the second reason why it's nice to have the center hole through it. I can tell when I'm all the way through. In this case, I came out of contact with the spring-loaded tap guide. I started to feel it move around, so I simply lower the spindle. This is where the spring-loaded portion comes inconvenient. So I lower it. Now it's going to maintain contact with my tap handle as I continue threading or cutting the thread into our workpiece. So I thread and I back up. I thread and I back up. I can feel the resistance drop. And I can see the tap has intersected our center hole. So I have threaded this in as far as I can go. So I back up. As I back up, I need to raise the spindle a little bit. So now I just unthread the tap out of the hole. Raise the spindle a little more. Okay, and now I'm all the way out, and I can raise the tap away from the workpiece, take the tap out of the way, and I can move the mill into position for the second hole, which is X0, Y, 1.25 inches, according to our part drawing. We're close to it again. As long as we're within a couple thou, we're fine. I'm going to repeat the process. I will wipe off the tap to wipe any chips off it from the previous hole. I'll reapply oil. There's a lot of friction when using a tap to cut threads, so you always want to have a lot of oil. I will put it back in I'll put the tap guide back in the tip of the end of the tap handle. I'll put the tap, start it in the hole. And now as I rotate the tap handle, the tap is automatically going to start feeding itself into the workpiece, cutting the thread profile that we desire. I'll lower the tap guide. I'm going to keep going. I'm going to back up when I feel a little resistance. That helps break the chips into smaller pieces that can evacuate via the 2 or 3 flutes along the axis of the tap. I can feel the resistance start to lessen, meaning I'm just about all the way through my part, and I can see that I've intersected the center hole. So yep, that's where I stop. I'll retract the tap, keeping the tap guide in contact. I don't want to raise the tap guide completely away, or else as I do this, I'm going to start to enlarge the hole and make the fit of the thread looser and sloppier and just lower quality. So I want to keep the tap guide engaged the whole way, in and out. You can see now why it's spring-loaded. That way we don't have to constantly raise and lower the quill, the spindle. We can just make a coarse adjustment, especially if we're just one person doing it by ourselves, and it makes it very convenient for us to use. So it's unscrewed all the way. Now I'm ready to raise it, remove it. I could use the air, and I could blow out the features. I could grab a 1024 screw, and I could check the fitment. Okay, whatever I need to do. But these two features are now completed according to our drawing. 0.157 through, that specifies the tap drill size, straight off the tap chart that we've given you for this course. And then it says 1024 UNC through, 2 places. Yep, so we are finished with these features. There are 3 similar holes on the rear face of our part. So we're going to clean up, remove the part from the vise, and then our next sequence will show clamping the part in the correct orientation, finding the X and Y datums, and creating the 3 holes in the face of the part for example, for the wheel to attach to. Okay, so we're going to stop here.